Hi there, in the last video clip I spoke about covalent bonding found in covalent gases or compounds, and they generally got low melting points and low boiling points. However, if I took some of these giant molecules such as sand, silicon dioxide, or another example, diamond, they've both got giant structures. Polymers, polyethylene, polystyrene, they've got very large structures, and these structures have therefore large amounts of covalent properties. So if I took something like silicon dioxide or sand, diamond, the girl's best friend, high melting point, high boiling point. Graphite is another form of carbon. It's got a higher melting point than a lot of other carbon compounds. Silicon dioxide, to you, sand. SiO2, there's a silicon joined to an oxygen. But then you've got the silicon joined to more silicon dioxide molecules, and you'd have more and more of these, and that one, that oxygen is joined to silicon, that's joined to oxygen, that one is joined to another oxygen, and there's another oxygen. So what you're getting is, this is a very large structure, and don't forget it's a three-dimensional structure. I've just drew it in 2 dimensions, whereas one molecule of the silicon dioxide is joined in 3 dimensions. Let's look at a second example of one of these large boys, something like carbon. Chemically, diamond is carbon, and the atoms of carbon are joined in a tetrahedron structure. Don't forget, these are in 3 dimensions. Like that is joined to that, is joined to that, and they're linked and joined in 3 dimensions in tetrahedral structures. Then that one, carbon, is joined to another carbon at a tetrahedron again, and that one would be part of another tetrahedron. That one there is another tetrahedron structure, like that. So these carbons are joined in tetrahedron structures in 3 dimensions. There's lots and lots of these bonds, which means they're going to have high melting points and high boiling points. Let's look at another example. Graphite chemically is carbon, and it consists of carbons, although I can't join it, that's supposed to have 6 sides, C, 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 C carbon, and these carbons are joined in hexagonal rings or structures. So there's the next one, C, 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 and I can go on and on and on. So graphite consists of a large number of carbon atoms. They're joined in a 3-dimensional structure, but unlike diamond, they're joined in a layer. So what we've got is, what is that? It's a layer of carbon atoms joined in hexagonal structures, another layer, another layer, another layer. But in the case of graphite, there's a delocalized cloud in which it contains electrons between those layers, like so. So therefore, graphite's got one special property compared to diamond: it conducts electricity. However, it's still got a high melting point and a high boiling point. Let's look at one more example. I just want quickly to mention polymers, plastics. I'll be talking more about this at a later stage. If I took a molecule of ethene, I polymerize, that by the way is a gas, I polymerize it, change it from a monomer into a polymer. All of those molecules become linked or joined, and there's another chain of ethene. The carbon links, and they are covalent bonds. It also contains hydrogen, but I'm not going to talk about that. It's like a set, if you like, beads. You've got your pearl of beads or chains of beads linked or joined in 3 dimensions. You've got, there's one polymer chain, a second polymer chain, and there's a force linking them together in 3 dimensions, intermolecular forces between that chain and that chain. That's why we change from a gas, ethene, into polyethene to form a giant covalent compounds. So I've spoken about 3-dimensional covalent compounds, specifically 3-dimension giant covalent structures: silicon dioxide, sand, graphite, C, carbon, and also diamond, a girl's best friend. But I'll be speaking more about the structure of these in a later video clip.